I'll go ahead and take over. All right, thank you. So I am going to talk a little bit, and then we'll have our Q&A section for the non-Saccharomyces portion. So I think everybody can see this. I'm going to talk about two experiments that we did at Laffort. Let me just make sure that everybody, can I get a head nod from somebody here? We good? I think we are. Okay. So what we did with the non-Saccharomyces is we got some highly compromised fruit from Elk Grove donated to us, and we wanted to implement a test where we would compare the addition of sulfur versus the non-Saccharomyces yeast in a laboratory setting at the UC Davis Research Winery. So Lucy and Leticia and Anita Olberholster were all really, really awesome at for letting us come in and do an experiment. And so we had some great consultation, and we started with some highly compromised fruit where the fruit was donated to us. It came to the winery, and we let it sit there for 3 days. There were fruit flies, just a ton of like really, it's not typically what you would want to make wine out of kind of stuff. So we waited 3 days, and then we processed the fruit, dividing segments of the fruit into different TJs or bioreactors at UCD. And so we had 6 bioreactors, 2 triplicates, and in one group we had a 60 ppm add of sulfur, and then in the other group we had a blend of non-Saccharomyces yeast, including Meshnicoia and Torulaspora. So we did, the control was 60 ppm of sulfur, which is pretty common, that's kind of what you would normally see. And then the trial was 50 grams per hectoliter of non-Saccharomyces. And the analysis that we performed, the way that we quantified these differences in populations, was using qPCR with Rich Shinzo and Eric over at ETS. They were kind enough to get us some scorpions performed. So it's just that the yeast and bacteria scorpions that you'll see at ETS is how we quantified those. So briefly, Meshnicoia and Torulaspora, this is packaged in a 1-to-1 ratio. There's some really cool things that happen with Meshnicoia in regards to its cell morphology. It releases pulsarimic acid. It also sequesters iron. There's an interesting bit where it uses the pentose phosphate pathway as well. Some really great research at Washington State that got published on that for reducing ethanol content. But each of these organisms are selected, in this case, as a bioprotectant. The Torulaspora was part of an alpha project that we did. It has a positive aromatic influence. There's some weak proteolytic activity that Linda Bassan illustrated maybe 10 years ago. It's a known bioprotectant and has good implantation capacity. So we were just so happy to be able to work with UCD and all those people there on this project. So we have 2 sections of the project. The first part, we use good validation with ETS and UC Davis. And the second part of the experiment, we go out into the field and we try it on the vineyard. So let's talk a little bit about the compromised fruit ecology. So I'm just going to walk through what the data that we got back from the qPCR, what it kind of looked like. Acetic acid bacteria typically falls between 100 and 1,000 cells per milliliter. So when this is the control, so this is the SO2 bit. So on the x-axis, you'll see day 1 through 15. And then on the y-axis, you'll notice that's a logarithmic scale, and it's logarithmic so that I can see the totality of the data instead of just the baseline or just the top. So we go through the fermentation. There's just a ton of organisms in here. I could talk more about each of them, but I think Lucy's done a really good job talking about the complexity and how things are, how the organisms have their own identity, so to speak. So Hansenia spora comes in at 10 million cells per milliliter. This is, it's just nearly every organism that we can test for, we found, with the exception of Brettanomyces. So it looks really colorful. There's a lot of information on the graph. The important thing to know is that we can see trends inside the data. So the blue line there is the growth of Saccharomyces, and there are decay functions as Saccharomyces begins to build up the amount of ethanol in the system. The Hansenia spora begins to die. But if we look at it from a linear, on a linear axis, instead of having a logarithmic scale, we just transform and change the scale so that we have a linear axis, and we can see the amount of Hansenia spora is just incredible. It's a lot of pressure from the Hansenia spora, providing off characters during those first 6 days of fermentation before the Saccharomyces builds up its population to produce enough ethanol to kind of eliminate the Hansenia spora. Then if we look at the addition of our product, we see that the Hansenia spora is there's a lot less Hansenia spora here than there was in the control. And the reason that happens is because what we've done is after the cold soak, that 3-day cold soak, we add Meshnicoia pulcherrima and Torulaspora delbrueckii in such a massive amount, 30, I think it was 30 grams per hectoliter, no, 50 grams per hectoliter. We add this Meshnicoia and the Torulaspora to provide downward pressure. So we're utilizing the principles of competition to prevent the growth of unwanted organisms. Let's see. There we go. So when we put the two side by side, you can see that the control using 60 ppm of sulfur has a lot higher amounts of Hansenia spora. That's pretty easy to see. And then in our trial with the Meshnicoia and the Torulaspora, we see a lot less Hansenia spora, but we don't just see a lot less Hansenia spora, we see a lot less other organisms. And this is actually, we're taking this to the American Society of Enology and Viticulture, and we're hoping to publish this data. So some of the stuff I'm not going to include because those rights are going to be with Catalyst and the organization. Just to talk briefly about ASEV. ASEV is an organization that has really moved with the industry. They provide publication and peer review. They help tie research and the industry together, and it's a really great organization to be a part of, and we're really lucky to be able to work with them. So some of this stuff is not available, but what I can tell you is that it looks like we get good results, and each of the organisms respond a little bit differently. But what I can tell you is that the data is significant. When we look at the 2 treatments, I performed ANOVA along with some various other statistical methods. We do get a level of significance between the 2 treatments at 0.09. So the data is significant with a p-value less than 0.1. So we can reject the null hypothesis that there is no difference, meaning that we accept the alternative hypothesis that there is, in fact, a difference between the 2 treatments. So effectively, what we've said is that non-Saccharomyces species is better at controlling organisms related to wine spoilage than sulfur. And that's a huge statement because for hundreds of years, we've used sulfur as an antimicrobial, but not just an antimicrobial, but also an antioxidant. And we'll talk more about that later. What we see is that 10 times the normal dosage does increase some of the sensory characters. So we wanted to use a huge dosage to see if we could inoculate a surface. So we'll get to that. We're always looking for new partners. We'd love to have you guys on board. But let's get over to the living harvester. So we had a winemaker come to us and she said, my harvester smells like VA. What can I do about that? So we built a air rifle, a blaster that shoots yeast approximately 17 feet. And we used the blaster as a way to inoculate the harvester. If you imagine the harvester is a surface, it's a vector covered with sugary water, grape juice, and it's a vector for wine spoilage, and it's just traveling through the vineyard. So instead of using harsh chemicals like ozone, which can affect the rubber components, or a toxic chemical like sulfur, we have a safe, non-toxic, non-GMO way to incorporate safe processes for not just the wine, but also for the workers who are using those products in the vineyard. It's easy to use. It takes about 5 minutes, and so we wanted to validate the data inside the laboratory at UC Davis, inside the research winery, and then move to the vineyard trials. And so the preliminary data looks pretty promising. We saw reduction of spoilage yeast at 10 to the 4 and bacteria as well. We're always looking to increase the robustness of this experiment. So the first year we got good validation. We tried it on the harvester, and now we're looking to expand the experiment. So we're gonna publish the results, and I'm sorry I can't show you guys everything, but that's just kind of the way it works. And move on into a larger experiment where we utilize multiple harvesters and multiple sites. With the vineyard trials, it's always a battle with variation. So we're battling variation by increasing our data points so that we can provide more robustness to the experimental design. So we've had some help. Lucy was really great, and Leticia Chacon at UC Davis. I got to give her a big shout out as well. We just had a really good time performing the experiment, and we look to find ways to innovate at Laffort. We want to innovate with our university partners and collaborate with the wineries that are interested in research. So all of you guys are here because you want to hear about the cool new research. If you want, you can reach out to your technical reps or to myself, and we can help you design products processes that will work with you. So we can do experiments and stuff. Here's my email address. You'll see it below the icon there. And at Laffort, like I said, we try to work with nature as much as possible. So let's switch over to the Q&A section, and I will start taking. Oh no. There we go. Let me see if I can do this. There we go. All right, so let's switch over to the Q&A section. So we had a question, Lucy, from Leah about the nitrogen requirements for for non-Saccharomyces yeast. Can you talk a little bit about that?
Of course, as I was emphasizing in the talk, that's going to be strain dependent, as with everything else. Um, their nitrogen requirements do not tend to be particularly high, but again, that's all a strain dependent thing. Those would all be things that if you're going to use a commercial product should have been looked at prior to usage. Because they're occurring early in the fermentation, the nitrogen is less of a problem because you're not going to run out of nitrogen before they're going to die off from the alcohol. So I think that's a valid question. I think it's something that's going to depend upon the commercial strain you're using.
Good, good. We had another question from Rick about alcohol production with non-Saccharomyces. The Trollospora and Mechanicoea, they only survive to 3 to 5, sometimes 7% ethanol. So those species will die off. There is some really interesting work on the Mechanicoea, where the Mechanicoea utilizes the pentose phosphate pathway in a aerobic environment instead of the fermentative pathway. So instead of producing ethanol, it can produce glycerol, and thereby reduce the amount of final ethanol. And this is similar. This is what Lucy was talking about when she was talking about cheating. And I think there was another word for it, Lucy. What was the other component besides cheating?
It's just utilization of the competitor's metabolites, and that's just what they call cheating. So the reduction in ethanol is certainly something that is prized, but you have to be careful of what it then takes it to when it doesn't make ethanol. What does it make? You don't want it to be making something that's worse in terms of the aroma, flavor.
And then we got a little bit more time. We're going to start with Stefan at 9:50. So 2 more minutes on questions. Let's see. Does non-sac yeast have an upper limit on bricks? Can non-sac be used on high bricks dessert wines like 45 plus bricks? Lucy?
So again, that's going to be a strain dependent thing, and it's probably true that there are some of them that are going to have more of a problem. Some probably less of a problem. There's one of the strains I talked about, Starmorella, is a fructophilic yeast. So it's going to use fructose preferentially. So that's, again, one of those niche metabolism things. So you're going to find some like that, some like Zygosaccharomyces, which are going to be much better at higher levels of sugar. And then you're going to find some that will probably do much worse at high sugar levels. So again, that's going to be a matter of the particular species and strain that is selected for that purpose. And there's a fairly large body of literature out there now on the different organisms and what they're good at.
Thank you, Lucy. So it's about time to start with Stefan Sommer. So I want to make sure that I give him a really good introduction. Stefan